morning was strictly monotonic. We've already talked about this monotone. Monotone's super boring. We learned it in pre-cal. It's only a function that doesn't change at all. In order for a function to be increasing or only be decreasing, the derivative sign is either only positive or negative. It could have some zeros, but it never actually changes direction in the sense of its behavior. And this was kind of just reiterating why we're looking for critical numbers. If a function is only increasing, only decreasing, the derivative only has one of these signs. But if a function were to change from this to this or this to this, then the slopes would have to change signs. And in order for the slopes to change signs, that can only happen at, IVT tells us, zeros. That can only happen at zeros or undefined. This bottom question, if a function is not strictly monotonic, can the function change from increasing to decreasing? Its derivatives, oh my, that's off, must change signs, which can only happen at zeros or DNEs of the derivative. And wait a minute, what are zeros or DNEs of the derivative called? So it's reiterating why we have to look for critical numbers, because they're the only spots where the derivative sign can change. So the function is only decreasing, the derivative only has one sign, but if the function were to change behaviors, the derivative sign will change, but that can only happen at zeros or DNEs, hence why we need to pitchfork. And once we have all that information, then we can go ahead and make a quick note to ourselves about discontinuities. This is critical numbers. We need critical numbers, but we can't forget discontinuities, as you guys saw in the page I just showed. They were analyzing for critical numbers, but also discontinuities, because we also need to include these guys in our sign charts. We have to keep them separate from critical numbers in our minds, but we do need to include them in our sign charts and in our analysis. Because technically, not just zeros or DNEs of the derivative, but also discontinuities. So there are technically two different places, critical numbers or discontinuities, where a function can change behavior. Discontinuities, I was reminding you in piecewise functions, if you have something like f of x equals g of x for x less than a, and h of x for x greater than or equal to a, there's going to be a discontinuity at the separator if g of a, sorry, not g prime, but if g of a, remember if they don't match up? So if plugging in A and plugging in A, if they don't match up, there's a discontinuity. If they do match up, it's fine. It's fine. And the other place we need to watch out for is anywhere where x cannot equal. So discontinuity is either where the function doesn't match up or where the x cannot equal. And then Thomas, you were talking about roles in MVT a little bit earlier and about the conditions. The rest of the class, that's a forever card. What are the conditions for roles in MVT? If f is continuous on closed endpoint to endpoint and differentiable on an open interval. So continuous, this, if it's a piecewise, do they match up, or are there any domain problems? Differentiable says look at the derivative, and you could say f prime, g prime, h prime. To be differentiable, these would have to match up, g prime and h prime. And then there could be no discontinuities or domain problems of the derivative. So continue looking at the original function. Differentiable looking at the derivative. Unless we have a graph and we can see a sharp point and say like, oh, look, it's not differentiable there. Okay, with that, let's take one more example. I did one on Friday where you guys didn't even have the steps written down yet. And I was like, hey, by the way, this tells us where the function is increasing and decreasing. But let's do another one real quick. So you guys just wrote down the steps, how to analyze for increasing and decreasing. You have a forever card that says a function is increasing where its derivative is positive, and a function is decreasing where its derivative is negative, and where its derivative is 0, it's neither. So the very first thing we would think about in our analysis is domain. Then we would think about critical numbers. Then we would make a sign chart. That's really it. 1, 2, 3. So, number 1, domain. Any problems? Nah, he's a polynomial. No square roots, no logarithms. X is between negative infinity and infinity. No big deal. And they don't give us any intervals, so sweet. Okay. Critical numbers. What do we need to find? This was what your homework was. Derivative. And then simplify it and pitchfork it. This one's easy though, right? So what's y prime? What's the derivative of any constant? Good, good, good. I don't need to pitchfork it, do I? Just set equal to 0? There's no denominator. We could simplify. Wait. Christina was right. Simplify. So 4x, we end up with x squared minus 5. Cool. What are my critical numbers? 0 and... yeah, plus or minus square root of 5. If it was a 9, it'd be plus or minus 3, but 5, oh well. It is what it is. Sign chart says take all this information, the domain, critical numbers, and go ahead and I'm going to go ahead and make a table, even though I'll show you the number line. There are a couple different variations. Where we have the intervals of, let's see, we have the test, then we have the sign of f prime, and then we have the behavior of f. So we're going from negative infinity to our first critical number, which is negative rad 5, then negative rad 5 to our second critical number to our third critical number. It's just like a number line. It's just like a number line. So some of you might want to use a number line analysis. That totally works too, because instead of doing this table, the table's nice because it shows you all the intervals so that once you get like a true false sort of thing or an increasing decreasing, you already have the answers already ready to go. However, you can also do a number line where you split up from negative infinity to infinity. You're thinking of the sign of f prime, behavior of f, and then you're splitting up at negative rad 5, 0, positive rad 5. It takes a little less work, but you also don't have your intervals ready to go for answers. So you could do a number line analysis, you could do a chart analysis. Let me show you what's going on though. In the chart analysis, we're going to pick a test number, root 5. Well, it's in between root 4 and root 9, right? In between 2 and 3. So I could do, well, negative 3 then would be on that side. Negative 1 would be on that side, 1 would be on that side, and 3 would be on that side. Are those magical numbers? But that's just me and something, and I didn't want to choose decimal. So I figured out this is negative 2.6, so I was able to go ahead and straddle it with answers. And I had to choose something in between. Here, that would all happen in my head. I wouldn't actually write it out. I'd just be like, hey, what's something on this side? Negative 3, sweet, plug in. Plug into who? Plug into f. Now, could you plug in here? Sure. But, oh, gross. Who wants to simplify that? Hopefully, nobody. What would be easier to plug into? That one. Actually, technically, what would be even easier would be 4x, x plus root 5. This might be even a little bit easier to plug into. So if I plug in negative 3, that's a negative number. All I care about is positive or negative. Plugging in negative 3, negative 12. Plugging in negative 3, well, if that's 2.5-ish or 2 point something, that'd be a negative also. And then negative 3, a negative. So negative times a negative times a negative is a negative. What does that mean? The function is decreasing this whole time. If a function can only change behavior at these special numbers, at my discontinuities or critical numbers, well, what it's doing in one place is doing the whole time. We would have done this a little bit more in our head over here, plugging in negative 3, gotten a negative, and been able to say f is decreasing. Means the same thing. If we plug in negative 1, negative, negative 1 plus 2 point, that's a positive. So negative times a positive times a negative, positive, function's increasing. Once again, you don't have to do both of these. They're both valid. The differences. Or maybe the similarities. Plugging in 1, positive, positive, negative. A positive times a negative. and plugging in 3. Positive, positive. 3 minus 2.5, it should be positive. Now guys, they don't always change signs. Sometimes the entire thing will all be positive. Sometimes the entire thing will all be negative. It just depends. But on this one, they did change every other one. If this is the beginning of homework, you would just be answering where the function, where f is increasing and where f is decreasing. If you had to defend y, you would talk about, this isn't enough to defend y. You'd have to talk about, oh, the derivative is negative. F prime is negative on that interval. That's why the function is decreasing. Or f prime is positive on the interval. That's why the function is increasing. If you had to justify, you could put into words what this shows. But for right now, just answering, where's the function increasing? Well, from, you see it? Negative rad 5 to 0. And from rad 5 to infinity. And that we could do x is within. And then where's the function decreasing? You're just stealing what's in the table. Or if you're over here, you're writing what this whole interval of numbers, this whole range of numbers are. But either way, you should get the same answer. Decreasing would be negative infinity to negative rad 5. And then 0. This is the beginning of homework. If they just say increasing, decreasing. Maybe just a few of you, though, saw a shift towards the end of homework. I mean, some of you were just doing derivatives, which is all you had to do for homework over the weekend. But if you were reading the directions of the problems, you might have seen there was a little bit of a shift to not just asking for increasing, decreasing, but also relative mins and relative max. Can you guys look at that sign chart? And can you tell me where a minimum, not the minimum, a minimum could happen, will happen, does happen? Not negative infinity. Negative root 5. Why is there a min there? What's the function do at negative? Changes from decreasing? Oh, if there's a critical number, and more specifically a smooth turn, if there's a smooth turn here and it goes from decreasing to increasing, what kind of smooth turn did it have to be? A relative min. What kind of smooth turn's going on at 0? A relative max. And what's going on, what kind of smooth turn at rad 5? A minimum. How do you know? Because of the sign changes. And the fact that they were critical numbers, smooth turns. If they were sharp turns, they would have also been relative mins and maxes. And that brings us to the second part. Look at those relative mins and maxes. That's just the graph of the function. That brings us to the second part of section 3.3. How do you use the first derivative to identify relative extrema? Well, you guys just did it without this whole page. Get a sign chart. And we look at f prime signs, f's behaviors, and we identify, oh, hey, there must be a min, or oh, hey, there must be a max, or oh, hey, it looks like there's one, but there's not, because he's a vertical asymptote. Gets a little tricky there for a little bit, sometimes. Only critical numbers are candidates for relative mins and relative maxes. Are candidates. That doesn't mean that they necessarily are. They're the only ones that can legally become relative mins and maxes. Not discontinuities. Holes and vertical asymptotes can't be mins and maxes. We still need them in our sign chart, but they're not candidates. Only critical numbers, only smooth and sharp turns. You guys are thinking like number line, and you're thinking just like the shortcut version of the sign charts. Relative minimum, that's saying f prime changes from a negative to a positive at a critical number. It's the point at which the function changes from decreasing to increasing, or the derivative changes from negative to positive. We have to make sure we keep this. Negative, positive is with f prime. Decreasing, increasing is with f. If there's a critical number in between, then be a relative min at that critical number. If f prime changes from positive to negative, aka f changes from increasing to decreasing, if it happens at a critical number, there will be a relative max there. And if on a sign chart at a critical number, f prime does not change signs, whichever way it is, whether it's increasing to more increasing or decreasing to more increasing, there's no relative min or max there at that critical number. It might level off for a little bit, like a cubic or like a tangent. It might level off, but there's no min or max. So neither. Now the hard part is if you have your sign chart drawn, it's kind of really easy and you miss kind of some of what is going on as far as when the relative mins happen and the relative maxes happen. And we know the AP guys, they like to be. So they're not necessarily going to give you a sign chart and say, hey, what's there? And you're like, oh, it's a maximum. They might give you weird clues. And so getting down the actual wording and getting down how f prime, we're looking at the signs of f prime, and f, we're looking at the behavior, etc., is going to be good. This is called the first derivative test. I put in parentheses for relative extrema because as we learn something called the second derivative test, we lose the fact that we're looking specifically for relative extrema. At the very bottom, there's just a reminder. F has to exist at that point. If this is not a critical number, if this is like a vertical asymptote or a hole, that's not a min. If this is not a critical number, if this is like a hole or a vertical asymptote, this is not a max. So at the bottom, I can't have mins and maxes at discontinuities, which is why the very first thing we always do is ask ourselves, domain of the original function. It can be a sharp point. The derivative cannot exist. It can be a sharp point. The derivative cannot exist, but the original function has to exist to have a min. So quick example, if I was to have something like f prime and f from a positive to a negative, so an increasing to a decreasing, if this was something like a horizontal asymptote in between, what could be going on? Say that my point in my sign chart was right here. It didn't come from a critical number, or it was a discontinuity first. I can have increasing. I can have decreasing before and after a vertical asymptote, but there is no maximum because the vertical asymptote is what splits up those two. So there can be a sign change at a discontinuity, but there's no min or no max, so we have to keep an eye open for domain problems. Guys, help me out. I'm totally off with the new week starting. This is forever number 21? 22. Oh, because increasing, decreasing test was 21. Increasing test, decreasing test is 21. You don't need to necessarily write this down unless you just want to remind yourself. It's not for the forever card or anything like that. The forever card ended above that last note. But to have a relative extrema, a relative min or a relative max in between or over like an open interval, we have to have a sign change of the derivative. We have to have a change of the function from decreasing to increasing, which is indicated by a sign change in the derivative. But as we just saw, not every sign change means a relative min or max. Domain problems can make it seem like there is when there isn't. And here's a second one. Just because you have a critical number, once again, does not mean that there's a relative min or max there either. You have to check for a sign change. Critical numbers are candidates, but there's no guarantee as to what they are until you do a sign chart. So the steps, you don't even really have to write much. Because the long story short, the steps, to figure out the increasing, decreasing nature of the function using what we just talked about. And then analyze it and say, are there any mins or maxes in there? And you kind of follow the movement, and whenever you see what could be a min, that's not a min, sorry, what could be a max, you have to double check and say, ooh, is that a domain problem? No? Sweet, there's a max. Whenever you see could be a, oh, is that a domain problem? No? Ah, sweet, there's a min. Done. So it's nothing really extra besides just going one step beyond. So if we were to take, I don't know, ooh, these don't look very fun. But you guys in your homework saw ones that weren't fun, right? You maybe saw some fractional ones, maybe you saw some piecewise ones. We're going to use the first derivative test to identify any relative extrema of these two functions. I'm going to give you guys just a second to get ahead for the derivatives. Remember this weekend you were doing this work in your work 19A derivative simplified. I'm going to do it back here because I'm going to model if you have the derivative solved somewhere else, how you can use it to finish homework tonight. I'm also doing the derivative for the second one just so we can have it quick. Okay, so with these derivatives, I'm going to go ahead and say, kind of like you guys, pretending from this weekend, for all those numbers that I wrote, and the other ones that I didn't write, you have a graph or you have something different where you don't necessarily need to be finding derivatives. Here's what you can do in your homework when you go to do homework 19 on a new page in your homework spiral, right? You could say, hey, I'm not cheating. I already did the work and I have the derivative. And the derivative is, okay, this is where it's going to be nice. The derivative is, you should have it on your little derivative simplified paper. Okay, now, once you have the derivative, before you go to the sign chart, because either way you need a sign chart to analyze the behavior of f through the signs of f prime, you're going to have to ask yourself two questions. One is domain, looking at the first one. The other one is critical numbers, looking at the second one. Okay, domain, looking at the first one. Are there any domain problems? Good. The original function x cannot equal plus or minus 3. Technically, since they're going to be numbers over zeros, those are vertical asymptotes. They don't cancel out with the numerator. Critical numbers. Pitchfork. Why am I just putting 0 even though there's a plus or minus 3 in the denominator? Their discontinuity is good. They're domain problems. So I'm going to put them in my sign chart, but they're not critical numbers. They don't exist. They're not really there. They can't be critical points if they're not points. So once you've, well, hopefully, you can look at your homework 19A and just steal out the derivative simplified. Boom, there he is. Critical numbers, domain, let's go. Sign chart time. Sign chart time. I'm going to do this one with the sign chart and that one with the number line just to show you both. So sign chart time. If you actually do the chart, we would go ahead with our intervals, which would be negative infinity to negative 3, negative 3 to 0, 0 to 3, and 3 to infinity. Those are using all of my different domain problems and my critical numbers. We're going to pick a test value in each of those. We're going to do the sign of f prime, and then we're going to do the behavior of f. And if you want, you could even do like I/D, increasing, decreasing, or INC/DEC of f. That's specifically what we're looking at. So if I was to go ahead and pick test points, I don't know, what do you guys think? Negative 4, negative 1, 1 and 4. Is that easy? Where am I? So the derivative's up here. If I plug in a negative here, a negative times a negative is a positive. Anything squared is always a, so a positive over a positive. Take as much time as you need on that, but we're going to have a positive. If you want to, you just keep on doing all your signs and then come back and figure out your behaviors. So if I plug in -1, that's a positive over a positive, that's a positive. If I plug in 1, a negative over a positive. If I plug in 4, a negative over a positive. So I end up with increasing, increasing, decreasing, decreasing. Now at this point, you don't necessarily have to do the graphs of these. You don't necessarily have to do the graphs of these guys. That's not what they're asking. They're not asking for you to do like a full-on sketch. That's coming towards the end of the chapter, or the end of chapter 3a. But they are asking you to find any relative extrema. Now, where's the only place 1 could even happen, like according to the behavior of this? Yeah, and what is the point in between these two intervals? 0 is the boundary point. So it looks like there's a relative what at 0? Yeah. But what do we have to ask ourselves first? Wait, does 0 exist? Yeah. Okay, so that's good. Yeah, there's going to be a relative max. Equals 0. If you had to justify, you could say since f of 0 exists, f prime of 0 is 0, and f prime changes from positive to negative at that point. Could have also said x equals 0 is a critical number of f and f prime changes. Those are the two conditions that need to be true. I just kind of fleshed out what a critical number means in that I'm saying like, oh, okay, he exists and f prime is 0 equals 0. And the sign change is all enough justification. AP is all about, can you build your case? A case that's airtight that no one can say like, oh, wait, but. And that builds the case for why there's a relative max. So when I come over to this guy, isn't it nice if we can just look over at our derivative simplified work and say, oh, sweet, okay, the derivative is f prime of x is equal to negative 2x and negative 2. Guys, why is there no equal 0 in this piecewise function for my derivative? Did you see what I was analyzing off to the side? I said, hey, for things to be continuous and piecewise, I need the two sides to match. So I checked the derivative from above and I checked the derivative from below. I said, are they equal? And no. So therefore, there is no derivative at 0. The derivative does not exist at 0. So hold on, we have to ask ourselves two questions. Domain, any discontinuity problems? Any discontinuity problems or domain problems? And then critical numbers. Now, domain problems, this says negative infinity to 0 and 0 to infinity, including, there's no domain problems. This is actually, this exists for all values of x, but are there any discontinuities? Because if a function is discontinuous, if the function is not continuous, the function isn't differentiable. So we could check it. Plugging in 0, I get 4. Plugging in 0, I get 0. Does 4 equal 0? Do these two match up? No. So there's a discontinuity at 0. Domain is all real numbers. Domain's no big deal because everybody has a point, including 0. He has a point too. But they just don't match up. There's a discontinuity. Here, I can then say, okay, f prime does not exist. Wait. Okay, f prime, that's technically a critical number. We can just put in parentheses because f prime does not exist. But remember, f prime equaling 0 or not existing is enough to say it's a critical number as long as the domain, as long as the point exists. So we have a critical number, x equals 0. Sign chart time, but let me go ahead and do a number line this time. Some of you might prefer this. I'm going from negative infinity to infinity, so my number line is forever left, forever right. I have a 0 in the very middle. I'm saying, what's the sign fine. I'm trying to think about the behavior, increasing, decreasing of f, if that helps. In my head, I would say, what's something in between negative infinity and 0? Negative 1. I would plug in negative 1, and negative 1, well, doesn't that put me in this interval right here? So I plug in a negative, and a negative 2 times negative 1 is positive, right? So I can say, oh, sweet, positive. And I can plug in a positive 1, which would be in this interval. Well, plugging in, that's just always negative 2, so that will always be a negative. Huh. So the function is increasing before and decreasing after? The function is increasing before and decreasing after? Is there? If we're putting in our increasing, decreasing, if they were asking for that, I could say the function is increasing from negative infinity to 0. I could say the function is decreasing from 0 to infinity. What seems to be happening at 0? It is discontinuous, that's true, but it does exist. F of 0 does equal 4. Maybe think about what this guy is. 4 minus x squared, isn't that a parabola that's shifted up 4? And it's closed there. And then negative 2x, isn't that down here? Struggle. So it is discontinuous, but it has points everywhere. At x equals 0, it's x. Is it the highest of the points all around it? Kind of. Right? Because if I look before, it's higher, and if I look after, it's higher. The weird thing is the discontinuity, but am I allowed to have a relative max at or when f prime does not exist? Yeah. But it's not a sharp turn. It's kind of like a smooth turn on one side and a sharp turn on the other. Is this a relative max? I'm going to leave you guys hanging on this one because I want to get to one more example. I want you guys, when you're doing homework, to see if there are any other ones like this, where it's like, well, there's not a domain problem, there's a point, but there's a discontinuity. I wonder if that makes the relative max illegal, or if I still say it's a relative max. Keep an eye open in homework. Let me know tomorrow if you can see any other ones, or if you find any other ones. It should only happen in piecewise functions. But I want us to do one last example, but which one do I want you to do? Let's do a motion example, because it'll have us practice. Yeah, let's do a motion-y problem. It'll have us practice this process one more time. And I'll give you one quick warning before we're done for today as far as what else you might see. But this will have us practice the idea one more time, but in a different application, which is where homework, I think, ends. So guys, look at the directions. They're crazy, they're long. But the function's really not that bad. So it says, like, hey, by the way, this is a position function. Okay, fine. Find the velocity function. What's that another way of saying? Yeah, find f prime, or this guy prime, technically s prime, right? So s prime of t is going to be the velocity function, or if you want, you could say, you want me to find velocity. Okay, I'll find velocity by finding s prime. This guy's pretty easy, 3t squared minus 40t plus 128. Can I pull out a 3? No. I can't, right? Ugh, that's sad. Okay, but I find the velocity, aka the first derivative. Letter B says, identify the time intervals in which the particle is moving in a positive direction. What? Time interval? That sounds like a sign chart, but positive direction, what does that mean? Where the position is increasing, aka where the velocity is positive. It's the same thing as a sign chart. So I'm going to talk about my domain, but my domain is all real numbers of time. Unless it says something about, oh, no. Time starts at 0, which kind of makes sense, I suppose, in most examples. So we're going to actually have the domain be 0 to infinity because of what they said. So in my sign chart, I'm going to start at 0 and go to infinity. This is what we do when there's like a limited. But wait a minute, to do a sign chart, to figure out the signs of velocity, aka the behavior, the increasing, decreasing of position, don't I need some critical numbers first? Even though they didn't tell me to do it. I should have factored this guy. Factored him? Are you kidding? Well, if worst comes to worst, if you don't want to think about the factor 128 and 3, that might make 40, end up with, what would that be? 360, 384. You have to think. Couldn't you always do t equals negative b plus or minus square root b squared minus 4ac all over 2a? Critical numbers, you would put them to the side. Positive direction is velocity positive, negative direction is velocity negative. Changes direction, those are just critical numbers. Relative extrema. Kiddos, in your homework, all I want you to do is, as you're walking out, keep an eye open for what if they give you the derivative instead of the original. You're not going to have to find a derivative. If they give you a derivative instead of an original, you don't have to find a derivative. You take what you've been given. All right, kiddos, homework number 19 for tomorrow. Yes. Yeah. What are you making up, though, Thomas? Remind me. Which one are you making up?
16 and 17.
Got it.